So the goals of this talk are to quickly go through what EXES is, what kind of data it produces, and a review of the data products from the archive. And that means the URSA archive. And then part two, how to correct telluric absorption in the data using both real data on on-sky telluric calibrators and then using synthetic calibration tools like ATRAN and the planetary spectrum generator. And then I had to restrict this further to our most common types of observations, and this will so be focused on just knotted observations of point-like sources in the EXES high, medium, and high-low modes. So I'll quickly describe what that means. So EXES in a nutshell is optimized to be a high-resolution spectrograph, and it is cross-dispersed. Here you see 3 different ways that we can get the same resolution data at about 13.7 microns by changing the cross-dispersion order. And we label the 2 situations at the extremes, high, medium, and high, low, because of the grading angle and the fact that the blaze on the grading switches modes, switches actually facets on the grading. But that's the detail behind the scenes. The point for you to know is that at the same wavelengths, you can choose to maximize your spatial coverage while getting a very narrow spectral window. This is about 8 orders here. Or you can choose to squeeze in as many spectral orders as possible onto the 1024 by 1024 detector, like the extreme on the right, by shortening the slit, but then you lose spatial coverage. And the practical difference between these 2 modes is on the left-hand panel with a 20 arcsecond slit. You can fit a SOFIA point source, actually several SOFIA point sources along the slit. So SOFIA at these wavelengths is producing images of about 2.5 arcseconds. But on the rightmost extreme, you're actually losing light from a PSF that size. So you have to be interested in a very bright source to consider that mode. One thing I wanted to point out is the resolution is totally the same in all 3 of these depicted modes. It's controlled by the other grading and the slit width that you select. So it can be between 50,000 and 100,000 spectral resolution. EXES does not chop the secondary mirror for its sky subtraction. Instead, it uses slow nods of the telescope between A and B coordinates at a frequency or period of about 30 to 120 arcseconds. And this is absolutely necessary because the sky is overwhelmingly bright in molecular emission and in thermal background from the telescope optics, maybe a couple thousand to 100,000 times brighter than the source that you might be looking at. So I show we start out on the B position on a point source, and then we do the A position. They look exactly alike in the raw data, and only after subtracting the 2 do you see a star beam filling up the 8 orders along this echellogram in the raw data. And also point out early that there's no guarantee that you get complete subtraction of the telluric features. The sky doesn't have to hold still for you. So you can see at the core of these strong CO2 lines, you see over subtraction from the peaky bit from the high part of the atmosphere, good subtraction from the wings. And it's just something that you have to hope averages out because we don't have the ability to chop and get near simultaneous sampling of the sky. So for this purpose, I think most people should be interested in the EXES 1D products if they're interested in point source observations. And for that on URSA, select in the program that you're interested in, select the MRD, the order merge products, and also the CMB and the SPC files, which are order unmerged. And the structure of those data files is listed below, where EXES works in wave numbers, or the data products are in wave numbers. The second plane is flux. I'll have the units on a note in the next slide. And then the variance of that flux. And then it includes a pasted on ATRAN model that hasn't been adjusted in any way to the atmosphere other than having it share the same wavelength scale as the spectrum. And here's a couple preview images from produced at URSA, or actually produced by SOFIA and sent to URSA. And there's an AGB star with some CO2 lines, and you can see a light gray trace here, which is the ATRAN model, and it mimics the features, the dominant features in the spectrum, but doesn't get all of them because there's real emission in this source. And then here's an example of an order unmerged product where the orders are plotted on top of each other in different colors. And this is an H2 emission line, but it's being kind of chopped up by a strong telluric residual from the atmosphere. It's methane at 8 microns, but the line is in the clear. It doesn't have much telluric interference, so it's perfectly usable, and we planned it for the date that it would be so. So a little bit more about the EXES 1D data products. Wave number, if you're not used to using it, is convertible to wavelengths by dividing it out of 10,000, and that puts it into micron units. The standard flux unit is ergs per second centimeter per wave number. That's like a Jansky, and I guess it's flux density. And you can convert it to Jansky with just this factor if you work out the conversions. Looking through the different planes in a 1D spectrum file, this is what the order unmerged can be, what it looks like. You have a little bit of overlap between the orders. I color coded them for the eight orders stretching across here, and then I put in the ATRAN model at the top. There's a little bit of disagreement of the flux at the ends of the orders where the counts go low. But in general, the second plane takes care of that by keeping track of the noise in the data. So when this product gets order merged, it will basically ignore the high noise parts that are starting to fall off, but not completely. And we do recommend that you work with both order merged and order unmerged products to make sure that you're not being fooled from some sort of like low count regime effect on the continuum. And the last plane is that ATRAN model that's looked up and pasted into the data. And again, it's not adjusted in any way to the conditions of the observation, just it shares the wavelength solution of the observation. So a little bit more about the nodding. I wanted to window in on that residual emission issue, because there's differences in different modes. And I also included what our flat fields look like to take out the order shape. So we have a very luminous black body source that we take a brief look at before the observation to find our orders, but also to trace the blaze efficiency across the orders. And then again, this is the A and the B of a point source nodded observation that looks exactly the same because the thermal emission overwhelms anything from the star. And then only in the difference do you see it. And if you look closely, there's residual emission and kind of staining the spectrum at all the positions where there was sky emission. But because we were able to take it in a A-B nodding on slit mode, there is a recourse for this, which we can force a condition for A and B to sum to 0 across the slit, and then remove all the residuals, and then you get a nice spectrum at the end where if you combine all these, you should have something that reflects real only telluric absorption in the atmosphere. And no residual emission. Alternatively, if there was only one beam on here, we would find a place on the slit for a background subtraction. It works a little bit less well, but it is effective. But there's situations where we can't necessarily remove sky emission residuals, and that's where we're observing a extended object. Here's a protostellar emission line, a protostellar outflow that creates an H2 emission line that has extended structure. It doesn't have, it's in a position where it's not really being affected by telluric absorption, but it definitely is stained elsewhere in the oscillogram by a strong residual from methane, which seemed to get weaker through the observation, creating a residual. And the other case is when the slit was chosen to be so short for maximizing that instantaneous wavelength coverage. Then you don't really, you're counting on it canceling at the end of a long sequence of nods. So this is a spectrum of IRC 2 towards Orion with a strong residual from carbon dioxide. And we'll see this again and see that it's really not that bad once you start dealing with it, and if you know what to ignore. So now into the section where I want to show you how I use real calibrators taken on sky. These aren't regularly taken, not like in the near infrared where people bracket their observations. That's just not operationally feasible for SOFIA at all times. But when they're available, they can be convenient. My example, it comes from a published result from Odwin Bogart's program from cycle 4, looking at a deeply embedded binary protostar called MONAR2 IRS3, and looking for resolving a sulfur dioxide band that's known to be there with low resolution, medium resolution spectra from ISO. So the important things when you download this data are to get an idea of the altitude of the observation and the altitude of the matching Sirius observation that was taken on the same program to have as a divisor, and then pay attention to the zenith angle so that you can adjust air masses. The air mass of MONAR2 is slightly less than Sirius, and we'll use that in the next panel. So the steps I take are make sure that Sirius is on the same wave number scale as the science target, MONAR2, normalize the flux of the calibrator Sirius to 1, and then adjust the normalized Sirius for the air mass differences. That means thinning out the telluric absorption in Sirius by taking it to a power less than 1. It should have been, I think I have the order of these numbers wrong. It should be 2.3 minus 1.74. But nevertheless, be prepared to refine it further, because that's what you expect, but the plane has moved by like 300 miles during the observation, so even if it shares the same altitude, things change. So be prepared to trust your eyes. The result is there's a pretty flat spectrum of MONAR2. And you can see clear signatures of the sulfur dioxide running through it. And I also indicated where the water absorption is putting these big fat triangular absorption features in the spectrum. And then this is what was originally impacting it, the HRAN at the bottom in red. So you see, especially in the line cores of the methane, there's still some residuals, and those regions should be ignored or not trusted. But there's a lot in here to use. So switching to the much more common case where a telluric calibrator was not available or not schedulable, I divide this into 3 cases, or options really, where you can, in some cases, just use the canned HRAN model that comes with the 1D spectrum, or you can download a new model from HRAN and or planetary spectrum generator, and then try to adjust it to the data. So for that first case, and you can kind of guess that it has to be kind of a simplifying case, where the example I drew here is a Betelgeuse observation taken just in December with permission from the geo. I'm showing it here. This bright ionized iron line is caught in about a third of the way down in a strong water absorption line in the atmosphere. And actually the canned HRAN model is able to mimic this by putting it to a power of 0.68 perfectly adequately. It doesn't matter that the HRAN model doesn't get the resolution right, because resolution doesn't matter for telluric features this broad. This is probably 100 kilometers a second across. So it doesn't really matter the sampling or the resolution, you just adjust it by a power. And you can see it flattens it suitably well to get a decent flux and profile on that iron line. Some cases are you need to go a little bit more carefully, and those are particularly where there's narrow telluric features cutting through your spectrum. So this example is another published result, this one from the program by Nassim Rangwala, published by Sarah Nickerson just last year. And the source is Orion IRC2, associated with a protostar, maybe its outflow. But for us, what I'm concerned about is at these 14 micron wavelengths, the atmosphere is cut up by these repeating CO2 lines and then narrow O3 lines. And we need to get the resolution absolutely right if we want to somehow divide those out. So some instructions that I won't go through too carefully in this presentation, but hopefully there's enough in the slides that you can follow later. When you go to download the new HRAN and PSG models, take note of the header information on the altitude of the observation. That's the most important one, I think, because it affects the broadening and the profile through the atmosphere for getting a kind of the correct line structure, so that you can at least get it right when you take it to a power. The zenith angle isn't as important, but it's good to know what to expect. We generally I go about adjusting that with an exponent anyway to get it to agree with what I see. But this is how to convert it to an air mass. And just a reminder of what air mass does to the transmission looking up versus at an angle through the atmosphere. And then note the wavelength, or actually wave number extremes taken from the spectrum file. And on the HRAN site hosted by SOFIA, these are the parameters that you enter. This is where you enter the feet of altitude. If you don't put in a water vapor overburden, that's often okay. It'll guess a typical value. And actually, what I'm trying to correct here doesn't really have any water in it at this particular wavelength. And then I have the wavelength extremes. And then entering 0 gives the highest possible spectral resolution of the model, so that I have something that's only broadened by like natural physical processes, and then I can Gaussian broaden it to what I want. The output of this, once you download it, is just 3 columns, where you want the second 2 columns, which is just wavelength in microns and transmission. And now PSG has a few more panels to visit. Actually, the tool does a heck of a lot, and you have to find deep in there that there's a template for telluric transmission, and then find the window where you change the altitude of the observation and define the spectrograph parameters. I plan on updating this SOFIA cookbook in progress with working with Steve Goldman to have these details, but he's done a lot for an automatic retrieval that should be available sometime this year. But the end product and the advantage of using PSG is that it separates the individual molecules by contribution to the telluric absorption. And you see in this small window, the key absorbers around 14 microns are, just like I said before, CO2, but both broad and narrow components of it, and then O3. And then the blue is something they call collisionally induced absorption, which I didn't really know about, but should be included too. And you can basically ignore the contributions of everything else, but this gives you leverage to individually adjust these column densities. So the output, as I said, is going to be a bunch of wave number, a total absorption from all molecules, and then an absorption from each individual constituent. And then the other thing to note as you're tuning these models to your data is the slit, which sets the resolution of the data. There are only 4 slits that we'd use regularly for EXES, going from R of 100,000 with the narrowest to R of 50,000. But here's where I note, and this is something that I've only come to appreciate in the last year or two, is that at the long wavelengths, we start to see sharpening of the resolution at the longer wavelengths. And the inventor of the instrument, John Lacey, and I talked, and he thinks that it's because of slit diffraction, where as light passes through the slit, the profile that hits the grating is softened and sharpened onto the detector. So it effectively sees a narrower slit at these long wavelengths. So be prepared to trust your eyes and increase the resolution at these long wavelengths. And by long, I mean greater than 10. I don't see this effect very much at the shorter wavelengths, and basically you get the nominal resolutions. So going back to the IRC2 spectrum, here in the black at the bottom, I did an adjustment of this R of 500,000 PSG model. The adjustment for ATRAN or PSG is the same, so I'll just show you the PSG. It comes out extremely sharp at the natural broadening of the physical lines in the atmosphere, then broadened to the nominal slit width of the observation, which was R of 50,000, by looking at closely spaced lines in the IRC2 spectrum. I can see that R of 50,000 really doesn't represent it well by how the line is more blended in that model. So I adjusted upwards to a resolution of 63,000. And then here's a note in the corner here for getting the right Gaussian width to apply using a Gaussian smoothing tool that I use in IDL. And this is after all the tinkering that I could do of all those individual constituents in the atmosphere, mainly just CO2 versus O3, each of them getting their own exponent. And then after that adjustment of the resolution. And what I saw is that I can do a slightly better job on removing narrow lines with the PSG, but it does a really awful job around the CO2 lines, which might have something to do with the fact that the CO2 lines aren't just absorption, they're residual emission that happens to be negative. You can see that by the way that it goes 0. But for some reason that I don't quite understand, ATRAN is able to represent those line widths, but at the cost of having more residuals around the narrow lines. So this part of the spectrum that I'm showing you is not an interesting part of the spectrum. It's where there was no molecular absorption in the source IRC2. So to look at what the real purpose of this observation was and what Sarah published, I show the region around the hydrogen cyanide Q branch and see what you can pull out of these spectra. actually both do sort of an adequate job of getting these lines to a place where you can draw a continuum on either side of the HCN lines and get a good width and depth of the line. So that's what I wanted to show you. That's about all I know about calibrating EXES data.